Welcome to Spring LIB.
So this is the answer to Chapter 12, problem number 48 from the Smith Organic Chemistry textbook. And this problem is asking us to show the product of a series of reactions, and then it's asking for a stepwise mechanism. So first, we'll take a look at what the products are going to be. So you have this molecule with a double bond and a bromine. And so you're going to firstly treat it with MCPBA. And so that's going to epoxidize the alkene, as we know. And so that's your first product, is this epoxide. The bromine's still there. Bromine's just fine. Then next, you're going to open the epoxide with hydroxide ion in water. And so you're going to end up making a diol, which I've drawn here. And then after that, you're going to treat it with sodium hydride, which is just acting as a strong base here. And we'll take a look at the mechanism in a second, but that's going to end up giving you this molecule here. So an oxygen-containing 5-membered heterocycle with an alcohol on it. And so when we go to look at the mechanism, what I've done here is I've drawn the molecules in black, and I've drawn lone pairs of electrons and arrows showing the flow of electrons in blue. And so first, the MCPBA comes in and epoxidizes the alkene. And so remember, with an MCPBA epoxidation, it is a single step. So all of these arrows are happening at the same time in a single step. And you can see the flow of electrons from one of the lone pairs on this oxygen to this carbon that's double bonded to another carbon, but then the electrons in that double bond flowing back to the oxygen at the same time, which is how you end up making an epoxide. And then at the same time, this oxygen-hydrogen bond is breaking, and this oxygen-oxygen bond is breaking, and this carbon-oxygen-carbonyl bond is grabbing the hydrogen from this oxygen. So it's a bit unpleasant to look at, but that is correct. They do all happen at the same time. And so next, so we have our epoxide, and we're going to open it with base in water. So the hydroxide ion comes in, and so there are 2 other lone pairs on this oxygen, and I guess I should just get them in there just to be consistent. I have omitted lone pairs where they're not really participating in any way, but it is always good to just draw all of your lone pairs and to be consistent. And so a lone pair of oxygens on this hydroxide ion is going to attack the least substituted carbon of the epoxide, and then that carbon-oxygen bond in the epoxide is going to break. Those electrons are going to revert to the oxygen. So that takes us to our next intermediate, where we have 1 alcohol and 1 alkoxide. And so this oxygen has a negative charge on it now. It has 3 lone pairs of electrons, and I did draw them just for clarity so that you can see where the negative charge is coming from. So one of those lone pairs of electrons is going to pluck a hydrogen from a water molecule, and of course that OH bond will revert to this oxygen, and so we'll end up with a diol now. And then so lastly, at this step, this is where the sodium hydride has been added. So remember, hydride is a hydrogen molecule with a lone pair and a negative charge. And so that's what's happening here. It's a strong base, so it's going to pluck this hydrogen from this alcohol to make hydrogen gas. The electrons in this OH bond will revert to the oxygen. So that takes us to our final intermediate, where this oxygen is now an alkoxide with 3 lone pairs and a negative charge. And one of those lone pairs is just going to do an SN2 attack on this alkyl halide. So this carbon right here will be attacked by a lone pair on the oxygen. The electrons in this carbon-bromine bond will kick off to the bromine. The bromine will leave. And that's how you end up with your heterocycle down here, your final product. And so this is the answer and the mechanism for problem number 48.